Yeah, okay. So I did get one question. Let me pop it up uh, about the latest prelim. It's no, that's it. Yeah, okay. So it's number 5. Um, yeah, so this problem here, so there was the last homework problem on the final homework. Remember, does say that actually Fn goes to F and L infinity is equivalent to that Fn goes to F uniformly on some on R takeaway A for some set A of measure 0. This is just a little easier basically. So the original sequence does work, but you need a lot more work to do that. We're not, I mean, it's a little trickier to do that. Um, but the idea is basically you can't just immediately say, oh yeah, clearly the Fn goes to F uniformly anywhere. Because what does convergence in L infinity mean? And I'll get to that right now. Let me go to the whiteboard. Oops. Yeah, so Fn goes to F. L infinity really anything. I mean, it means basically this limit here. It means this limit is 0. Uh, so what that basically means is, so I'll kind of combine. Uh, well, yeah. So this here is an essential upper bound. Of Fn minus F. So for any epsilon bigger than 0, there exists n. Little n bigger than big N implies, I'll write it like this. So this is an essential upper bound of Fn minus F. And just by, really just regular convergence, of, of numbers, a sequence of non-negative numbers to 0, this is less than epsilon. And so the key here is for almost every x in R. But what this means is for each n, we have that the set where this is false has measure 0. So all we can say is, let's say, whoops. So for n bigger than n, if, I don't know, let's say B for bad, I guess. If B, say Bn epsilon is going to be the set where weird. So let's say it's a set of all x bigger than epsilon. Yeah, so this is going to be equals, right. Um, right. So probably, so is this making sense here? This is essential upper bound, so this holds for almost every, I'm not sure if that got cut off here, but yeah, so all you can say is this holds. So as long as little n is bigger than big N, this holds for almost every x. This is true for almost every x. So the measure of this set is 0. So everything okay so far? Particular Andrew, does that make sense?
So far, so good. Yeah.
Yeah. Yeah, so the easiest thing to do really is Zoom is being really annoying as usual, blocking a lot of my stuff. There, okay. Yeah, so just set let's say instead of epsilon, we have 1 over k. And not that it matters, I'd probably make life a little easier, just make bigger or equal to. You could just do nk plus 1 otherwise. Um, yeah, so right, so this is going to be true. So in particular, just setting little n to be nk, we could make our lives a little easier. Let's say bk is this here. Yeah, make this 1 over k. Yeah, okay, so bk is the set of all x where fnk of x minus f of x bigger or equal to 1 over k. Then this certainly has measure 0. So I take the union. That's kind of what makes all these kind of problems work, is union of sets of the countable union of sets of measure 0 still measure 0. Even the double countable union of sets of measure 0 is still measure 0. That's how you do the harder version of the last homework set, which was I think 2019 it was asked. But
So,
sorry, so it's for any k yeah. So right, so yeah, take your n equals nk, that's fine. So let's say I guess I use A in the problem. So let's say A is this union. So if X is in our takeaway A, so it's in each one of these. Our takeaway K. K. Yeah, so then right, what is true F? Um so I mean yeah, I should technically let me do one thing just to make sure, minor thing, just to make sure you actually have a subsequence, because these don't necessarily I guess you can even say, just that loss of generality. I mean, this is not a big deal. Because if anything, you just take the maximum of everything prior and add one. But anyway, we've done things like this before. And this with loss of generality is thanks to we can let little n be anything bigger than big NK, and this is true. Yeah, this is fine. Yeah, so X for any K, X is not in BK. So it's not in BK, so this is less than actually less than 1 over K. And that tells you that you have uniform convergence of you could do the whole epsilon, pick an epsilon, then pick a K, pick a K bigger than epsilon. So I guess like might as well do that. Yeah, okay. So if say yeah, so this is, I mean, again, this works for any K whatsoever because we're away from all of these BKs. We're in this intersection here. This is going to be less than 1 over K. And that's less than 1 over K tilde. Yeah, and this has nothing to do with X. We're just picking arbitrary X in our takeaway A. And as long as literally this is true, we're good to go. Yeah, any questions or issues with this problem? Again, the key is this is true almost every. That's as good as you can get. That's fine. Because we can take countable union of sets of measure 0 and still get something that has measure 0.
So if we wanted to prove that the whole sequence has a desired property instead of just a subsequence, would we parameterize B instead of by what you have it originally as K and epsilon? Um, or you would essentially replace epsilon with a 1/n sort of number, and
Um,
then demonstrate that it's a double countable union and therefore a countable union.
yeah, I can go over it, that solution.
Oh, I don't personally not necessarily need to see it, but as long as that's the gist.
It's you still you really can't work with epsilon. I mean, it's probably easier just to, yeah, I'll just quickly go over it just because it's a little easier to maybe explain it. Um, it's you would really take full use of the bigger equal to get a double, like an actual double union. Let me just yeah, okay, let me just do this. This is really annoying. Um, So I think a little slightly different notation, but yeah, make sure I'm sharing this. Yeah. Yeah, so you'd start off the same way. Pick epsilon is 1/k. And then you get exactly the same thing here. As long as n is bigger or equal to, doesn't matter. That means that this is true almost everywhere. X and 0 to 1 realigned, that doesn't matter one bit. But the problem, I think this was, yeah, number 7, 2019. This was on 0 to 1. So yeah, you got to be a little more careful, in particular, take absolutely full advantage of this. And I think the cleanest way to do this is the exact same thing, but stick a plus J here. And that basically, we're taking full advantage of the fact that this has measure 0 for each J and each K. But this is basically saying, yeah, it's saying that, literally it's saying this here is less than 1/k for almost every x in 0 to 1. So, yeah, for nk plus 1, the set where this is false has measure 0. For nk plus 2, set where this is false has measure 0. Basically, all of these sets have measure 0. So this just represents nk plus 1, nk plus 2, nk plus 3, etc., etc. So yeah, you would want to take, it's not clear that this is going to work, but this is a reasonable idea to kind of try. We have all these bad sets. We want to excise all of them. And we can do that because we can do that and still have something with measure 0, because the union of all of these has measure 0. Still a countable double union, but still countable. Yeah, and you would set your set in the previous problem, it was A. So we want to prove uniform convergence on 0 to 1 take away E, where E is this double union. Again, it's not like immediate that this is going to work, but it's a reasonable thing to try. And it does work. So in particular, if X is an R take away E, then we're away from all of these, and that's pretty strong. So we do the similar thing. Hope it works. Does. Okay, I think you do that, I think on all of math, but in analysis for trickier problems, you do that sometimes. Just try something and hope it works. So yeah, K, pick K bigger than 1/epsilon. You get your N here. And if N is bigger than NK, let's hope, well, we have uniform convergence, regardless of what X is, Fn of X minus f of X should be less than epsilon. And it's going to be, because N bigger than NK means N is NK plus J for some J. Okay. But X is not in X is not in EJK because we're away from all of these. We're away from all of the EJKs. So that means directly this is less than epsilon. So yeah, it's just being a little more careful and taking full advantage of the definition of convergence. Does that kind of make sense?
That does, thank you.
Yeah. Does that make sense for anyone else? Because I mean, this is a tricky problem, but I mean, it's definitely, now that it's it'd be a little mean to have it for the first time, but occasionally we do put newer problems on that haven't been asked before. But it could be asked again because it is a previous problem, and once you see the trick, it's not that bad. So, any questions on this whatsoever? All right. Yeah, anything else in particular anyone wants me to go over? Any type of problem or anything really?
Could you go over like tricks with choosing the dominator for the Lebesgue dominated convergence theorem?
Sure. I mean, do you have a specific example you want me to?
I guess like just like the ones from the homework, I could never quite figure out like how you like you wrote it in the hint.
I mean, like, is it like a particular homework problem? Because there's a lot of different like types of you got like the Fourier transform is differentiable type. You got like the kind of ones where the dominator is just trivially less than or equal to the function itself, which is an L1. Or like using Borel-Cantelli, so you show something goes to zero almost every or the I think we had a dominate convergence theorem type with that. Like
I
anything in
think
particular you want me to?
could you go over the ones that also use Borel-Cantelli?
Um uh I might have to save that for next time because I might take me a minute to like go through these and see which one would use it. But you don't have like a specific problem in mind that like you kind of.
Let me see if I can find it.
Sure. Yeah, I mean I could do so actually yeah, I forgot, I'll send another email. But, so I do this one in video. Trying to remember one of the newer videos. And you can probably the easiest way to do this is density of well, step functions in L1, which is you really don't need that, just density of simple functions. A step function is a simple function. But yeah, you can do this with Borel-Cantelli. That's another way to kind of do it. I mean, I kind of tell you to do that. It's a little, yeah. I'll do this one. It's basically, I mean, it's a good exercise using Borel-Cantelli.
Is this the problem that you used as a lemma the other day? To prove, I don't remember what it was. It was a problem that had to do with absolute.
Yeah, exactly. Yeah. Did I prove that even Tuesday or?
You used this as a lemma. I don't think you proved it.
Yeah, okay. So the proof is yeah, okay. So the proof is in the um one of the absolute continuity videos. I forget which one. It's in one of the two, but I'll send, yeah. So yeah, I'll prove this using Burrell Contelli. It's a. Yeah. Yeah, the only annoying thing is you gotta be careful of your quantifiers when you do it this way, but that's fine. Okay, so right, so what are we trying to prove? Any epsilon bigger than 0, there exists delta. And I'm writing this in this kind of lack of English way because it makes negating like much clearer. Any subset of, I guess, R, because that's what the problem asks, but this works for any E, L1 of E. So this less than delta implies this. This less than epsilon. Okay, yeah, so we just negate trying to remember the symbol for negate, but all right, so this is what I copy this. So I don't know how to copy this. So let me just do this. I'm just gonna negate this. So I'm gonna start negating. So when you negate, I think the symbol is like this or the other way around. Whatever. So you negate this whole thing. What does epsilon for it's for all epsilon, what does that turn into? For all turns into what when you negate? So what I'm negating everything in parentheses here. So then for all epsilon for all becomes what when you negate? I remember.
There exists something that doesn't satisfy this condition.
Yeah, there exists. So you just do this one by one, like an onion. Here, I'll do this. This probably is not bad. It exists. And usually we just say epsilon 0, but you can still keep it epsilon. Okay, there exists turns into for all. Delta. For all becomes there exists. And when you negate an implication, it's this is false, but this is sorry, this is true, but this is bigger or equal to 0. So it's this and this negation. So That's just how you negate an implication. And yeah, so we're gonna get a contradiction from this. Yeah, so there exists an epsilon where for any delta, no matter how small, we can always pick an A, where this is nice and small, but this is still bigger or equal to epsilon. And intuitively, this makes sense that this is the negation of problem 1, August 2023. Yeah, and so you want to use Borel-Cantelli, so you pick delta to be 2 to the minus n, anything you sum up and it's finite. So let's say a k and this integral here is bigger, equal to epsilon 0. Right. Weird. Yeah, so this sum is finite. All right, so the usual conclusion, let's say there exists, you don't really need to, so let's just say, so for almost every x in R, x belongs. So what's the conclusion of Borel-Cantelli? One, remember? So this is finite, so for almost every x, what is true?
X belongs to at most finitely many a sub k.
Right. A's. So for such x, there exists n a bigger than n. No claim of uniformity here as usual. So n definitely is going to depend on possibly x. Well, it possibly will depend on x. That's fine. But k bigger than n is going to imply that x is, well, would imply what? If it's only in finitely many of these sets, then we're eventually gonna have that what is true about x and AK. So yeah, x belongs to finitely many of these AKs. So then you can find a big N. So eventually, basically, x has what relationship to these AKs? not gonna be in AK, right? That should make sense. It's only in finitely many of them, so eventually it's not gonna be in them. And so that means so K is bigger than N. Say Fk of X is defined as this characteristic function. Yeah. This is going to be equal to 0. So for almost every X and R, we've proved that this limit here is going to be equal to what? So what would this limit be for almost every X and R? Well, it's going to be 0 because, I mean, X is not an AK for, yeah, so X is not an AK for K, for some K, for K large, particularly there is an N where if K is bigger than N, then X is not an AK, so the characteristic function is 0. So Fk is going to be 0 for large enough K. How large has to depend on X. Okay, but yeah, so here is like, this is where like you have a trivial dominator, because it's just F is assumed to be an L1. So this is less than or equal to F of X. Okay, so this limit here has to be 0. Okay, here. So just interchange limits and integrals. Well, that's a contradiction too. Remember, this is just absolute value of F times characteristic function. And we picked the AK, so it's bigger or equal to some epsilon 0. Like there exists an epsilon 0 where this is true for all K. Yeah, so we get a contradiction if we assume the statement is false. We have a contradiction to Lebesgue dominating. So yeah, this is admittedly much simpler if you do the density of step functions in L1. There it's almost trivial. But this, I would say, just understanding this is a good exercise and a lot of stuff we're doing. So as inefficient and I would say overly complicated as this doing it this way is, it's just good to understand, I think. Yeah, and I'll send an email on which of the absolute continuity videos I precisely do this problem using density of step functions, really. Just need simple functions, but. Does that, any questions on that? Does that kind of make sense? Is there, another particular dominated convergence theorem problem you want me to go over?
So
There
the
was-
ones, sorry.
No, you go ahead.
The ones from the homework were the sequential criteria for limits and the dominated convergence theorem. Like, so if I find like a question that I want for next time, should I just put in like the campus wire?
Yeah, you could do that, sure, and if, yeah, I can answer it there, or we can do it on Tuesday. Yeah, I mean, yeah, I can answer it there, and then if you have any, if you still have any questions, you can go over Tuesday, that works.
Do you still happen to have the written solutions for the final homework for the class?
Yeah, I think I sent that to everybody in the zip files.
I don't, was that a recent email? I don't,
Yeah, let me take a quick look and see.
because I thought that I had stupidly lost access to it because I forgot to look at it until after Brightspace was taken down.
Yeah, let me take a quick look. Sharing. Second. Alright, sent. Yeah, this was sent May 28th.
I see it now, my bad.
Yeah, no problem. Yeah, it would, I think this is basically everything. So. Yeah, and if it's something in this you don't understand, by all means, definitely good use of time to clarify. And if there's something I'm missing, definitely let me know. But I think this is everything. All right, yeah. Anything else? Go over. All right. Yeah, I'll meet again Tuesday. And yeah, I'll put this up on the playlist today. Yeah, I'll see you guys Tuesday then.
Thanks for doing this.
Yeah, sure thing. Yeah, take care.
Bye.
Bye-bye. Enjoy your weekend.